Hello, the topic of today's lesson is dynamics. In the previous video we studied kinematics, which describes how objects move. Now we'll explore why objects move by looking at the forces that cause motion. In this lesson we'll introduce Newton's laws of motion and explore key forces in physics: gravity, normal force, tension, friction, buoyancy, and elasticity. If the theory seems difficult, don't worry. Once you see it in action, everything will make much more sense. Feel free to take notes if needed. Let's get started. Dynamics is the branch of mechanics that studies the causes of motion. The principles of dynamics are described by Newton's three laws of motion. They form the foundation of classical mechanics and help us to understand everything from everyday motion to planetary orbits. Newton's first law, also known as the law of inertia, states: an object at rest stays at rest and an object in motion stays in motion with the same speed in the same direction, unless acted upon by an unbalanced force. The first law defines inertia, which is an object resistance to changes in motion. In other words, an object will keep moving the same way unless a force makes it speed up, slow down, or change direction. The same force can affect different objects differently, depending on their mass. This brings us to the three key concepts of dynamics: force, mass, and inertia. Newton's second law explains how forces cause motion. It states that the net force acting on an object is equal to the object's mass times its acceleration. Both force and acceleration are vectors, meaning they have direction as well as magnitude. In problem solving, we break this equation into components along the coordinate axis to analyze motion more effectively. Newton's third law states that if one object exerts a force on another, the second object exerts an equal force back in the opposite direction. A common mistake in problem solving is forgetting that these forces act on different objects. Newton's third law doesn't describe forces acting on the same object. Rather, it explains how two interacting objects exert forces on each other. Now, let's go over to the key forces in classical mechanics. Gravitational force follows the law of universal gravitation. But for most problems, we only need to remember that gravity pulls object toward the Earth with a force equal to mass times the acceleration due to gravity. By Newton's third law, when an object pressed against a surface, the surface pushed back with an equal force in the opposite direction. This force is called normal force and always acts perpendicular to the surface. A similar force is tension. If an object hangs from a string, the string exerts tension, pulling on the object. The tension force always acts along the string. Both the normal force and tension are special cases of elastic force. The elastic force is proportional to the extension or compression of a spring and is determined by Hooke's law. Another common force is friction, which resists motion when two surfaces are in contact. There are two types of friction: static friction and kinetic friction. Static friction prevents an object from moving when a force is applied. Kinetic friction takes over once the object starts moving and remains constant. Its magnitude is given by the formula. The last force we will discuss is the buoyant force, which follows Archimedes' principle. It states: an object immersed in a fluid experiences an upward buoyant force equal to the weight of the fluid displaced by the object. That concludes the theory, and now we'll move on to practice. So, first example. A block rests on the floor. The gravitational force acts on the block, pulling it downward. Since the block is in contact with the floor, it exerts a force on the surface. According to Newton's third law, the floor exerts an equal and opposite force back on the block. This force is called the normal force and always acts perpendicular to the surface. Initially, no other forces act on the block. When we begin to stretch a spring attached to it, an elastic force starts to act. This force increases proportionally to the extension of the spring. Since the block remains stationary at first, there must be another force opposing the motion. This is static friction. As the spring stretches further, the force pulling on the block increases. At a certain point, the block starts to move. This happens when the static friction force reaches its maximum possible value and can no longer hold the block in place. At any moment from the start of the spring's extension to the instant the block begins to move, four forces act on the block. Since the block is at rest, the sum of these forces must be zero, according to Newton's first law. We can express this mathematically using a vector equation, but in practice it's easier to work with projections of forces onto the coordinate axis. Gravity mg and the normal force N are perpendicular to the x-axis, so their x-components are zero. The elastic force acts along the x-axis, so its x-component is positive and equal to its magnitude. The friction force acts opposite to the direction of motion, so its x-component is negative. We apply the same approach to the y-axis. From this equation, we see that normal force is equal in magnitude to the gravitational force. The elastic force equals the friction force while the block remains at rest. At the moment the block begins to move, the friction reaches its maximum possible value, which is given by the product of the coefficient of friction and the normal force. The elastic force depends on the spring constant K and is proportional to the extension of the spring. This means that at the moment the block starts moving, the following equation holds. By measuring the extension of the spring at the moment the block starts moving, we can calculate the coefficient of friction, which describes how much friction the surface provides. Let's move on to the next example. This example will help us understand how buoyant force and tension in a string work. So, a block hanging from an extendable, massless string while submerged in water. Three forces act on the block: gravitational force, tension in the string and buoyant force. Since the block is at rest, the sum of these forces must be zero, according to Newton's first law. All forces act along a single vertical line, so we only need one coordinate axis to analyze projections. We set the y-axis pointing upward. Forces directed upward will have positive projections, while forces directed downward will be negative. From this, we can express the tension force acting on the block. Now, let's consider a cylinder attached to the other end of the string. The cylinder also experiences three forces: gravitational force, tension and buoyant force. Since the string is massless, the tension acting on the cylinder has the same magnitude as the tension acting on the block. However, this is one key difference. The cylinder is not fully submerged in water. According to Archimedes' principle, the buoyant force is equal to the weight of the displaced liquid. So in the formula, we use only the volume of the submerged part of the cylinder, not its total volume. Since the cylinder is also at rest, the sum of all forces acting on it must be zero. We write Newton's first law for the y-axis and express the tension force. Equating this tension to the one acting on the block gives us an equation that connects the masses of the objects and the submerged volumes. Since the block and the cylinder are connected by an extendable string, they can also be treated as a single system. By applying Newton's first law to the system, we can write an equation that describes equilibrium. If we project this equation onto the y-axis and substitute the expressions for the forces, we arrive at the same result as when we analyzed the objects separately. Now let's consider what happens if the string is cut. The moment the string is cut, the tension force disappears. As a result, the block will sink and the cylinder will rise. We can determine the initial accelerations immediately after the string is cut. Let's analyze the block first. We apply Newton's second law and project it onto the y-axis. Since the acceleration of the block is directed downward, its projection will be negative. This allows us to solve for acceleration of the sinking block. If we know the initial height of the block, we can use kinematics to find how long it takes to reach the bottom. You can try calculating it yourself. Now let's look at the cylinder. Apply Newton's second law along the y-axis. We see that its acceleration is positive, since it moves upward. As the cylinder rises, its submerged volume decreases. Eventually, buoyant force equals the cylinder weight, and it reaches its equilibrium position. Due to its momentum, the cylinder overshoots its position. As it keeps rising, buoyant force becomes smaller than gravity, slowing it down and pulling it back. This back and forth motion creates oscillations. Since oscillations are beyond the scope of this lesson, let's move on to the next example. Let's consider a block resting on an inclined plane that forms an angle alpha with the horizontal. Three forces act on the block: gravitational force directed vertically downward, normal force acting perpendicular to the surface, and friction force, directed up the plane along the surface. Since the block is at rest, the sum of these forces must be zero. To analyze the forces, let's define a coordinate system. Now let's project Newton's first law onto this axis. From these equations we obtain two important results. First, the normal force is equal to the y component of gravity. This is a fundamental result you should be able to derive by yourself. Second, if the block remains stationary, the friction force is equal to the x component of gravity. If we gradually increase the incline angle, the x component of gravity increases as well. Since friction adjusts to match this force while the block remains at rest, the friction force also increases. At a certain critical angle, the block starts sliding. At this point, the friction force reaches its maximum possible value. Thus, by measuring the angle at which the block just begins to slide, we can determine the coefficient of friction between the block and the surface. Now let's consider what happens if we increase the angle further, causing the block to slide down with acceleration. The same three forces act on the block. To find its acceleration, we apply Newton's second law and project it onto the x-axis. Since acceleration is directed along the x-axis, its projection is positive and equal to its magnitude. The y-axis projection remains unchanged, so the normal force is still equal to mg cosine alpha. The friction force is given by the formula. Solving this equation for acceleration we get. Notice that the acceleration doesn't depend on the mass of the block. It is determined only by the inclined angle alpha and the coefficient of friction. Let's move on to the last example. A block suspended by a string in an accelerating elevator. Two forces act on the block, the gravitational force and the tension force in the string. According to Newton's second law, the sum of the forces acting on the object is equal to the product of its mass and acceleration. Let's direct the y-axis upward and project the equation onto this axis. The gravitational force is directed opposite to the axis, so its projection is negative. The tension force is aligned with the axis, so its projection is positive. The acceleration is opposite to the axis, so its projection is negative. From this equation it's easy to express the tension force. Notice that in this case it's less than the gravitational force. The magnitude of the tension force is exactly equal to the apparent weight. If the block were not suspended in an elevator, but placed on its floor, the apparent weight would be equal to the normal force. If the elevator were slowing down, the acceleration would be directed in the opposite direction, and its projection would be positive. As a result, the tension force, and therefore the apparent weight, would be greater than the gravitational force. If the elevator were moving with an acceleration equal to the acceleration due to gravity, the apparent weight would be zero. Thus, in a free-falling elevator, objects experience a state of weightlessness. That's all for today. Thank you for watching. If you have any questions, feel free to leave them in the comments. I'll try to answer them. Don't forget to subscribe to the channel and leave a like. See you in the next video.